Hello physics students. In this video, we're going to expand on what we did in the last video, which was study the behavior of conductors in static equilibrium. So basically what we're going to do is just look at conductors in even more situations in static equilibrium. So in this video, there will be no calculations. Everything's going to be conceptual. I'm just going to be drawing diagrams and talking about how conductors behave in various situations. Now remember, in the last video, I gave you 4 main ideas or truths about conductors in static equilibrium. So let's review those before we move on to today's scenarios. The first is that the electric field inside the metal of a conductor, where the atoms are, is 0. Okay, and again, that's only for static equilibrium. If you put a battery on, that's not true anymore because there'll be electrical flow. But in equilibrium, electric field is 0 inside. Related to that is that the electric field at the surface of the conductor is always perpendicular to the surface of the conductor. A third idea is that all excess charge that's on the conductor will end up residing on the surface, the very surface of the conductor. Or surfaces, I should say, if there's more than one. And the fourth idea, which is a consequence of the electric field ideas, is that the entire metal is an equipotential. In other words, if you find or calculate delta V between any 2 points, either 2 points on the surface or 2 points inside, or from the surface to inside, if you integrate negative integral E dx or ds, whatever you want to call it, between 2 points, you always get 0. The entire conductor is an equipotential. All right, so those are the 4 ideas which we'll be using to expand our understanding of how conductors behave in equilibrium. So the first thing I want to do is just do a couple things that are kind of review. We already talked about this a while back in a previous unit. This idea that you can charge a conductor without touching it by a charged object. It's called charging by induction. And there's 3 big steps to it. What you have to do is you have to have a conductor that's connected to the ground. In other words, a wire that runs into planet Earth. And then you bring a charged object near that conductor. What will happen is if this is negative, it will repel some of the electrons out of this metal, or all of them, I should say. But the difference between a conductor and a non-conductor is that the electrons can now move. They're repelled and they can move because it conducts electricity. So these electrons go as far away as they can and they start migrating through this wire and go into the Earth, leaving 4 protons without partners if 4 electrons went into the Earth. The second step you do is you remove the ground. So you pull this wire off, and now these minuses are stuck in the Earth, and then when you take the charged object away, the original negative, now this conductor is positive. It became charged without ever being touched by a charged object. That's charging by induction. If you did not remove this ground wire, and then you took that negative object away, what would happen is those minuses would come back and neutralize. So it's critical that you remove that ground wire in step 2. So, and another thing I want to point out, this also works if you bring a positive charge near. But before I do that, I'm going to distort the diagram. I'll give you a moment to copy this down before I start messing with it. Okay, so suppose instead, and by the way, don't copy this yet because I'm going to alter that so even though you could see it. So let's suppose instead I bring a positive charge here instead of a negative. What will happen now is that this conductor, any electrons that are in this conductor will be attracted this way, and they'll sort of shift this way, but instead of the 4 electrons being repelled into the Earth, these came from the Earth. In other words, electrons now move in because they're attracted to this positive. So, and by the way, you don't have to redraw this. We're just kind of I'm showing you that it doesn't matter. The effect works the same whether you bring a positive or negative charge nearby. So now you remove the ground wire. Oops. Oh. Got to wait for it to dry. I made a mistake. So there's minuses here. Now you remove the ground wire, and then you take away that original positive object, and these electrons that were brought out of the earth now are stuck in that metal. So it works just the same. Another thing I want to review is, so positive induces a negative charge, negative would have induced a positive charge using charging by induction. Another thing I want to point out is that neutral spheres are attracted to charged objects. Using Coulomb's law, if you use F equals K Q1 Q2 over R squared, you would think that with one of the charges being 0, the force between the two objects should be 0. However, because, again, this is a conductor, what happens if I bring, for example, a negative near this metal, the electrons will be sort of shifting over here on the outside, leaving some protons over here without partners. Now these unpartnered protons are attracted to this negative. These negatives are repelled from this negative. However, this force is larger because it's closer to the minus than this one, which is further away, so the repulsion is smaller, and there's a net force to the left, an attraction. Same thing would happen with a positive here. It would attract the neutral sphere also. Okay, so another interesting thing about conductors. Okay, moving on here. You already copied this down. So again, you're not copying this down yet. What I have here is an electric field that's uniform. As we can see, pointing to the right, how do we tell that the electric field is uniform, in other words, constant? We could tell that because these arrows are all equally spaced apart. If electric field lines get closer and closer together, the field is getting more intense. If they're spreading apart, it's getting weaker. So this is equal concentration everywhere. Now, what happens with another interesting thing a conductor does is it can shield, or it does shield, electric field. So electric field shielding. So what I'm going to do is now imagine that I put a conductor in this space. So what I'm going to first do is make some room with these electric field lines. So well, that was supposed to be a sphere. Let's try again. Well, a little bit better. Let me touch this up. Okay, and get rid of this electric field line also. And maybe this one also here. Now I'm erasing the electric field lines, but for now they're still there. I just plop a conductor in this region. The conductor is made of protons, electrons. The protons can't move because they're in the nucleus of the conductor, but the electrons can. That's why it's a conductor. So electrons feel a force in the opposite direction electric field. Electric field's this way, so the electrons feel a force this way. What happens as a result is that, let me think about colors. Let's see. Yeah, maybe I'll do, it's blue. The electrons migrate to the left, and what happens is we've got electrons now here, and since this electron came from here, it now left a proton behind unpartnered. So there's a little bit of positive here without a partner. So this electron came over here. There might be another electron here that left an atom from here. Same here. And then maybe something like this, and there's an electron over here, and an electron down here. And that's probably good enough. What I'm trying to show, and I hope it shows, is that the concentration of charges is greatest here and it gets weaker further out. But what happens is, the original electric field is like this. Now all of a sudden what happens is, these charges within the metal make their own electric field. And so I'm going to draw these fields, but again, don't draw this yet. I'll tell you when. This is the original electric field. These create their own electric field from plus to minus. And you see that there's a canceling effect. Does it exactly cancel? Absolutely. Because if it didn't, let's suppose the field was weaker. That means there's still a net electric field like this, which means even more electrons will come over here, leaving more protons over here, lengthening that blue arrow, and that continues until they exactly match, and then the E net inside equals 0. So we already knew this, that the electric field inside a conductor in static equilibrium is 0. Okay? That also distorts the electric field out here. It used to come in straight, but see, if this electric field came in straight like this and hit here, it would not hit the surface of the conductor at a 90-degree angle, which would then cause electrons, if the E went this way, there'd be a component of the electric field that pointed this way, forcing more electrons this way, and making more electric field pointing this way, canceling that component of the electric field that points that way. So that means that these field lines have to adjust, well, they don't have, they're adjusted, I should say more accurately, by the metal so that they strike the surfaces at 90-degree angles. So these two are fine, but this one, as it's coming closer, it's going to have to curve in order to hit at a 90-degree angle. And then these had to have curved away to start at the surface at a 90-degree angle. This one here, maybe it even curves earlier, curves and hits at a 90-degree. This one here, oops, not doing a good job here. Curves, hits at a 90-degree angle. This one here, curved so that it started at a 90-degree angle. Having trouble today. Okay, let's try it again. Okay. There. There. This one here curves gently in and strikes at a 90 like that. This one here, try and make it symmetric with that one. And then try and make these have the same pattern but going out of the metal. Oops, I think I messed that one up too. Not bad, I guess. And then maybe this one curves in but never quite reaches the metal. Does something like this. Let's try and do the same thing here. Well, not bad, I guess. So that's the electric field distorted outside, everywhere, striking the conductor at a 90-degree. And I'm still not happy. These field lines should be more concentrated here than over here, and I'm not quite showing that very well. But hopefully you kind of get the idea. Now, not done just yet. Electric field is everywhere, 0 in the middle. That would be true even if you hollowed out the metal. So if I suddenly hollow this metal out so that it's like a cavity, the electric field in the cavity is still 0. Because again, all the charge resides on the surface. So taking out the middle doesn't really affect the surface and the way the charge affects this electric field coming in. This outer charge on this very outer surface right here still cancels the electric field whether there's a hole there or not. And that comes in handy. You could put things in the cavity to shield them from electrical effects and keep them safe. Because again, electrical effects, high electric field that we saw with the Van de Graaff, you could get a lightning bolt if it gets big enough, or it could electrocute you, right? So if you put yourself in a metal cavity, you're safe from everything happening outside electrical. Even if we're going to see in the next Van de Graaff video for today, even if this gets struck by lightning, boom, and now you think, I'm in metal, I'm in trouble. I'm in metal and it's struck by lightning, I'm going to get killed. You're safe. You're safe in that metal cavity because of this shielding effect. So what can we say about the summary? Maybe there's a little curvature here, but it's good enough. So we could say that so the electrons at the conductor surface quickly, exclamation, it happens very fast, they move to cancel the external electric field inside the cavity. Okay, so that's electric shielding. So now you could copy that down. Best of your ability. Hopefully you have better luck than I did. All my little mistakes and edits. All right, so you might need some time, so I'll create a pause here so you could catch up with that diagram. Okay, one other thing. The electric field need not be zero in a cavity. And you might say, well, aren't I just contradicting what I said? Well, this is canceling the external field. But if you bring a charge in with you, if this person had a proton with them, the cavity cannot cancel that charge in, because if I put a plus here and I put a Gaussian surface around it, Gauss's law is still true. I have a plus inside a Gaussian surface, there has to be flux coming out. So there must be field in the cavity if there's a positive in the cavity or a negative. Okay, so let's do this. Charge of, what did I want to do? Plus. Okay, so let me draw the shell here. We've got something like this. And this is plus. And the shell is negative. What will happen is if you make a Gaussian surface here, you would have flux coming out, electric field coming out. So what I'm going to do is, because the charge is +8, I'm going to try and draw 8 field lines symmetric like this. Not so good, that one, but. So far, I have not violated those 4 ideas about conductors and static equilibrium, mainly that the electric field along any surface is perpendicular 90 degrees to that surface. All these radially emanating field lines hit the inner surface at a 90-degree angle. Good. Okay, good so far. But now, what has to happen is that the electric field inside the metal has to be 0. But how could that be if I draw a Gaussian surface around like this? I'm enclosing that +8 charge. Well, we learned about this in Gauss's law. Negatives rush into this inner surface. Maybe I'll do them in a different color to highlight so they kind of show up a little bit better. Minus, 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 minus. And notice these minuses are symmetrically distributed around. And so when I make a Q enclosed like this, a Gaussian surface, my Q enclosed is +8, -8, 0. Electric field here is 0. Good, okay? However, right now I'm showing that the conducting shell has a charge of -8. And really, we said it had only -2. What that means is that there has to be, if there's -8, there has to be a +6 somewhere else. So we have the -2. Where does that +6 end up? It can only be on the surface, right? Excess charge must be on the surface of the conductor. The only surface left is the outer one. And furthermore, it distributes symmetrically. So I got to try and draw 6 charges plus symmetric. So let me draw 3, trying to estimate 120 degrees apart. There we are. And let me add 3 more in between. Okay, or I could have gotten a protractor out. Too much work, right? It's kind of estimated. Now, if I make a Gaussian surface out here, my Q enclosed is +6. So I have to have this proportional right number of electric field lines. If I had a 1-to-1, 8 microcoulombs was 8 lines, plus 6 microcoulombs, I got to make 6 lines to show conceptually the magnitude electric field. And this point goes radially outward like this. Oops. Wouldn't be complete without a little mistake today, right? Another one in this diagram. Couldn't be perfect, right? All right, so there it is. There's the electric field for these 2 shells, okay? These 2 charged objects. But one final point, something that's interesting about conductors, another thing, well, there's a lot of things that are interesting. The conductor shields the electric field outside from the inner region because of the way the charges move around. It turns out that the conductor also shields what's happening inside from the outside. Outside shield from the inside, what's going on inside ends up shielded from the outside. And so I'm going to do one more diagram. What happens if I were to take this charge and displace it so it's no longer in the center? Let's see what happens there. I guess I could have left it electric field shielding again, but I guess it's all under the same category. Let me try and repeat this shell. Okay, let's see if my luck continues. Bad luck. Well, it might be a little too big. Yeah, whatever. Good enough. Maybe I'll make it a little smaller. right here. Okay, and now I'm going to put this positive right here. It's still 8 microcoulombs. So I'm still going to draw 8 field lines coming out of that. So easy ones are these. Oops, easy. And here I go, I messed it up. All right, there. Now, why are those easy? Because they go straight out and they don't violate the rule that the electric field must be 90 degrees to the surface of a conductor. 90 degrees here, 90 degrees there, good, okay? But if I draw a line like this, straight up, see what happens? Here it doesn't hit at a 90 degree, no good. So I've got to curve this line so that it strikes this inner surface at a 90 degree angle. Maybe something like that. And the same with this one. I got to curve it so that it strikes at a 90 degree angle. And if I make a field line come out of here, it also has to curve to strike that surface at a 90 degree angle. And these two also have to, they can't go straight out. They're going to hit at a non-90 degree angle. So we got to go like something like this maybe. And there. 90 degree angles everywhere. That's why the field lines had a curve like that. So that's the electric field there. So far, so good. The next point. The electric field has to be 0 here. How can that be? Minuses have to rush into these field lines. And so now the minuses are no longer symmetric. See what happened? Here they were even. Now here they're more concentrated. Highest concentration on the far right side of the inner cavity. So now the electric field is effectively canceled. This positive is close here, so we got a lot of negatives here to cancel the electric field here. This positive's far away over here, so we don't need as many negatives here to cancel. Electric field canceled, everywhere is 0. That means there's no information once you get beyond this inner surface about where this is, because its effect has been canceled by the minuses. So once again, we need an excess of +6 on the outside, and that +6, as I said, has no idea where this is, so it goes even around. So once again, I'm going to try and draw 6 positives evenly around. So maybe like there's 120 degrees and 120 degrees. Not bad, I guess. Close enough. Okay. And then the electric field out here. Again, this effect has been shielded, so it's symmetric here. And I'm going to draw 6 lines. Why 6? If I make a Gaussian surface here, my Q enclosed is +6. So I'm going to make a proportional amount of field lines to indicate. There, okay? Notice identical, but the inside's different with the shift, okay? So one last thing is that we could write So let me create a pause to allow you to catch up with these diagrams. All right, so that's it for today. Again, what we did is we took those 4 ideas of electric field and conductors in static equilibrium. One was that the electric field inside of a conductor is always 0, inside the metal part. A related idea is that the electric field at the surface of a conductor must always be perpendicular to the conductor. And those 2 facts are caused by the fact that electrons quickly move around to cancel any electric field along in whatever direction they can move. So electric field, 0 inside the metal, it's perpendicular to the metal's surface or surfaces. And then the third is that all excess charge must always be on the surfaces, none in the middle, either on the outside or the inside, okay? And the fourth, that the entire conductor is an equipotential, meaning the voltage is constant all throughout the conductor. So then we looked at some kind of charging with charging by induction, and then the shielding effects, that external fields are shielded inside, and the effects of internal fields are shielded from the outside. So interesting thing about conductors in static equilibrium. All right, so I hope you enjoyed the video and my mistakes weren't too unbearable, the drawing and the erasing. I hope you enjoyed, and I'll see you in the next physics video.